All right, so the last part of section 9.2, we're going to do a little bit more with polar, and then we're going to tie in some stuff with parametric. Yesterday, what did I say polar was really good for drawing? Yep, circles, yeah. What did I mention would be complicated in polar? That we already have a system that it's simple. Yeah?
Linear lines.
Yeah, lines. So we're gonna look at how do you draw a line in polar. Okay? Not the easiest way to do it. Y equals mx plus b is much better. Okay? But you still can do it. All right, so remember how you write a point in polar. There's no x and y. It's an r and a theta. So I want to graph r equals 2. Okay, I want to try to do that graph. To do that, let's think of some points that would be on the graph r equals 2.
Bless you.
Hey, bless you. What would be a coordinate that's on the graph r equals 2? Any coordinate. Yeah.
2, 0 degrees.
2, 0 degrees. Yep. Right. Give me a few more. Yeah.
You could do 2, 90 degrees.
2, 90 degrees. All right. How about another one? Yeah.
2, 180 degrees.
Okay. 2, 180. I'm gonna keep going until we hit one that I'm looking for here. Can somebody give me another one besides those? Yeah.
2. Like 270.
All right. 270. Yeah. How about something else?
Do whatever. 245.
Yep. 245.
2360.
2360. Okay, that's the same as 20.
Isn't it anything 0 through 360?
It could be any angle 0 through 360. Yep. How about the radius?
-2.
-2. Right. So -2, and then you could pick an angle. Right. So keep that in mind. The radius can also be a negative number. If you go through all the angles with a +2, you'll hit everything anyway. But I just want you to remember that this is okay as a point, -245. All right, so let's graph. So we got 2, 0, 2, 180, 2, 90, 2, 270, -2, 45 degrees. Okay. So there's all your points. If we kept going and kept drawing more and more and more points, what kind of graph would we have?
A circle.
Yeah, r equals 2 is the graph of a circle in polar. And your calculator can do that. Okay, it can graph r equals 2. Now, when we graph something, you have like a point. Think of rectangular. You can graph just y equals something, and it's a horizontal line. You can graph just x equals something, and it's a vertical line. Okay? We're doing the same thing in polar. I started with r. R equals something as a circle. What do you think theta equals something will be? Yeah?
Just a line that 2.
It is going to be a line. So let's think of some points that could be on the graph theta equals 2. Anybody think of a point? Yeah?
2.
Okay, 2.
2.
2. Yep. Remember, that's radians in the second column. So 2, 2. What else?
10, 2.
Yep. 10, 2. I can't quite go that many circles out on this one.
2.
What is it?
0, 2.
I could do 0, 2.
Anything that has a 2.
Yeah.
Anything with the 2 on the right side, so it could be 1, 2, 3, 2, 4, 2.
Okay. What else?
-2.
Yes. And this time, if you don't do the negatives, you will not get the other part of your line. Okay. So 2, just to kind of give you an idea, 2 radians. You know, what is that in degrees? Well, it's 360 divided by pi. So it's about 114 degrees. Okay. So little bit past 90. So if we do 2 radians, we're right there. If we go 0, 2 radians, well, just stays right at the origin. If we go 1, 2 radians, 3, 2 radians, we're getting all of these. But if you don't do a negative radius, you won't get the other side of your line. Okay? So -1, and then rotate a little bit more than 90 degrees clockwise. Right about there. Right? -4, and then rotate a little bit more than 90. Right about there. Okay? So that's the line that we do. So graphing theta equals something, you will get a line that goes through the origin. But you can't really control it that much. You can't change with theta equals, you can't have it not go through the origin. Right? But what if I wanted it like have a y-intercept of a certain value? Well, with theta equals, you can't do that. That's not what theta equals will give you. All theta equals is going to do is give you lines going through the origin. Yeah, question?
How do you do like a piecewise function? So would it would it hit 0 if you wanted to?
You might be able to do some kind of piecewise function. We'd like to be able to do it in one function. Right? We'd like, if we could, somehow take something like this and convert that to polar. We had a formula yesterday for y and for x. What did y equal when we changed it to polar? Yeah?
It would be, y would be r sine theta.
Y was r sine theta. M. And what was x? Yep. R cosine theta. And when we put the calculator in polar mode, what letter has to be by itself to graph it? Like in function mode, it has to be y equals. How about in polar?
T equals.
So when we do parametric, it's x equals and y equals, and t is our parameter.
R equals.
R equals. So to graph this, you need r by itself. So we can multiply the r out. What would be my next step there to get r by itself? Yep.
Inverse sine.
That would do it.
Subtract the or yeah.
If you divide by r, it's just going to cancel it. If you
Yeah, we can't divide by r.
subtract by r, it'll also cancel it. This is a difficult one.
Oh, we're trying to do that.
Trying to get r by itself. So what do you have to do first? Yep.
How about sine? Can you take sine out of the left side? So
No, nothing with sine. That's going to kind of stay right where it is. Yeah?
How about we do something with the m and the r together? If we
Well, the mr cosine theta is one big thing. That's a term.
if we divide by the mr to the other side, no.
Yep.
Found guess would just be not like factored out, but just have the right side be one thing where it's like one times that entire thing. So it's just one. Because like I remember you saying the other day that for trig functions, like you can't just divide by sign, but you can technically if it's like only one thing on the other side or something. Like there's a certain circumstance where you can divide by trig.
Yeah, but there's r on both sides.
Right. What's the first step to getting a variable by itself? First, you have to get all the variables where?
One side.
You have to get them all on one side. So how would we get all the variables on one side here?
Minus mr cosine theta.
Yes. So you got a minus mr cosine theta minus Mr. cosine theta over here. Okay, Mr. cosine theta is gone. Now we have r sine theta minus mr cosine theta. Cosine theta minus mr cosine theta. Okay, so now we got all the variables on the left. What can I do now with what's on the left? Focusing on the r's.
Did you factor out again?
Yep, I can factor out an r. If I factor out an r, I'm left with sine theta minus m cosine theta. And lastly, how would you get r by itself?
Divide the sine theta minus m cosine theta by, or minus, or divide that, divide b by that.
Yeah, divide each side by sine theta, m cosine theta. And that is the equation of a line in polar. It's r equals b divided by sine theta minus m cosine theta. So b is your y-intercept, and m is your slope. So let's try it. Let's say you wanted to graph something in polar with a y-intercept of 3, and let's do a slope of 2. Just like y equals mx plus b, just fill them into that. So we have 3 divided by sine theta minus 2 cosine theta. I just picked those values for m and b. Okay, check your parameter. Make sure you're going from 0 to 2 pi. That looks good. I usually like to set my step at like 0.1. And as long as we did that right, it should cross the y-axis at 3 and have a slope of 2. You can notice how it drew it too. It didn't draw it the way we normally see a y equals mx plus b. It started, and because it's in polar, it drew this part first, and then went back and drew the other part. But now, if you take that, and you look at it, and you go back to function, type in the same thing now, but in y equals mx plus b, it should look exactly the same. So it's y equals 2x plus 3. 2x plus 3. All right, and let's compare. Yeah, looks the same. So this is the polar representation, and that was the function notation. So lines are much, much more complicated in polar. You need to know trig just to do lines in polar. That's why we normally don't, but you can. All right, any questions on that? If you make those two substitutions for x and y, you can take pretty much anything that's y equals, and you could convert it to polar. Parabolas, anything you want. Okay, so now we're going to look at another graph in polar. We're going to go beyond just lines and circles. To graph this one, we're really going to have to think about what's happening. We're going to have to break down the formula almost into like sections. Okay. So that's what I want to graph. 3 plus 3 sine theta. So first of all, it's r equals, and is the value of r constant? Is the value of r always the same?
No.
No, it's not a circle.
It's going to be the...
So it's a radius that's going to change. How it changes is going to control what kind of shape we get. This is part of a whole family of functions. Okay. We'll talk about what they're called in a minute. So we're going to graph this from theta min to theta max of 0 to 2 pi. If you don't go 0 to 2 pi, you don't get a full picture. So let's think about r a little bit. If theta goes from 0 to 2 pi, can anybody tell me what the biggest number you would ever get from that box would be?
2 pi. Or 360.
No, it's a nice answer. If you do the calculation in that box, filling in every single possible angle between 0 and 2 pi, I want to know the biggest answer you will ever get.
You're saying for theta.
Yeah? 6. Yep, 6 is the biggest answer you could ever get, because the biggest sine can ever get is 1. 1 times 3 plus 3 is 6. Now I want to know the smallest that the radius could ever get. Yeah? Okay, how about, we'll say, what's the shortest distance away from the origin the radius could ever get? Say it that way. Yeah? 0. Yeah. Because if sine was -1, that would be -3 plus 3. So yes, you could potentially get -6, but it would still be 6 units away. I'm looking for how close does this get to the origin. So at some point, the graph goes right through the origin, but at most, it's 6 units away. So if you had a window like -7 to 7, -7 to 7, you're going to be able to see this graph. That's why I just did that. Now, here's a graph of sine. That's going to help us to figure out what's going to happen if you triple sine and then add 3 to it. Okay, but we really have to understand what's happening to sine before we can triple it and add 3. And what we're going to do is we're going to break it up into 4 sections. Okay, we're going to look at the graph of sine from here to here, then from there to there, there to there, and then the last part. Okay, so I'm focusing on where we increase, decrease, cross the x-axis, and keep decreasing, and then increase again. Okay, so let's look at sine. I'm going to start by looking at the part in red. Okay, that's basically like your quadrant 1 angles. What happens to sine as you go from 0 to pi over 2? I want to know what happens to the, it's like the y value.
It increases.
Yeah, it increases. And what does it start at?
0.
It starts at 0. And where does the y value end
1.
in this section? It ends at 1. Okay, let's do that first for all the sections. How about pi over 2 to pi? What happens to the sine function on the green part?
It decreases.
From what to what?
1 to 0.
It goes from 1 down to 0. How about pi to 3 pi over 2?
0 to -1.
The sine function goes from 0 to -1. And how about, can someone else tell me 3 pi over 2 to 2 pi? Yep.
That'll be going from -1 to 0.
Hey. Okay, so now we know what's happening in each section to sine. Now we can triple that and add 3. And that's going to tell us what's happening to not just sine, but the actual radius in our picture. All right. So if we triple 0 to 1, what do you get? Yeah. You get 0 to 3, and now add 3 to what you just said. It goes from 3 to 6. So when we start sketching our function, in quadrant 1, for the angles between 0 and 90, the radius is going to start at 3, and it's going to end at 6. So the radius is going to grow in quadrant 1. Let's do quadrant 2. what happens if you triple 1 to 0? Yeah?
It's going to, when you triple it, it's going to be going from 3 to 0.
And then add 3.
It's going to be going from 6 to 3.
So the radius is going to decrease in quadrant 2 as we draw it, meaning it's going to start at 6 and it's going to curve back into 3. All right? When we triple 0 to negative 1, triple the sign, you get 0 to negative 3, and then add 3 to that. So if we had 0 to negative 3 and you add 3, that's 3 to 0. And then this bottom one is just the top one switched. So that gives us an idea of what's happening to the radius in each section. So is there any questions how we figured out what R is doing? Yep.
When I put into my calculator, like just you can go up a little bit. When I put the 3 plus 3 sine theta into my calculator, I put like 2 pi or 0. I just get 3. Like when I'm doing the second quit thing, like where it's the actual.
Well, we're not graphing it yet.
No, I know. Like for where you're actually like solving stuff.
Yeah.
I put like 2 pi. 360 and 0, and like the only answer I'm getting is 3, so I don't know which.
Well, if you put in 2 pi, the sine of 2 pi is 0. 0 times 3 is 0, and 0 plus 3 is 3. So that's why when you plug 2 pi in, you get 3.
And then for 0.
That's the same thing as 2 pi.
But then how are we supposed to be getting from 0 to 6? Because like
let's draw it.
Okay.
Okay, the radius never goes from 0 to 6. It goes from 3 to 6, 6 to 3, and then it goes 3
like
to 0.
above it. Yeah, the 0. The radius was like 0 to 6. How do we get?
Oh, the radius. Well, you'll see when we sketch. Okay. So in quadrant 1, what is the radius at 0 degrees or 0 radians? What is the radius? Yep.
3.
3. 0 degrees, the radius is 3. How about at pi over 2? What's the radius? When we get all the way to the end of quadrant 1. 6. Okay, so when we go 90 degrees, we're up at 6. So what's happening is the radius is growing the entire time as you rotate counterclockwise from 0 to 90. So you can think of it kind of like this. The radius is getting longer and longer each time. That's kind of what's happening. Okay, so the radius is growing. Okay, so that's what's happening in quadrant 1. Okay, something kind of like that. Now in quadrant 2, what's the radius when we're at 90 degrees? 6. It's picking up where it left off. And as you rotate to 180, what does the radius decrease to?
To 3.
Goes back to 3. So it's going to look just like this one, except reflected. Okay, so I'm just going to take that, make a copy of it, and I'll flip it. Okay, so kind of like that. All right. Now let's look at what happens in quadrant 3. When you're at 180, the radius is 3. Oh, did I put that on the wrong spot?
You put it on -4.
Did a little bit off there. And I'm a little off over there too, which is why that's okay. All right. So what's happening to the radius in the third quadrant? It's going from what to what?
3 to 0.
It's going from 3 to 0. Where is the radius of 0?
The origin.
Right at the origin. So what's happening now is it's going to go right into the origin. So it's going to start being 3 units long. And as you rotate around, the radius is getting shorter and shorter and shorter till it ends up basically going right into the origin. All right. And now what happens in quadrant 4? The radius goes from what to what?
0 to 3.
It goes from 0 to 3. So how is this side going to compare to this one?
I think the same thing.
Yeah, it's going to just be kind of like a mirror image of it. So it's going to come back out. Let's put that there. It's going to go from 0. And as you start to rotate, the radial lines get longer, 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 till you get all the way over here. And then they're back where we started.
Wait, what coordinate system are we graphing this on?
This is polar.
Oh. But why does it like flat instead of just like going straight?
Why does it what?
Like why does it have like the curves underneath instead of just like straight?
Because the radius is getting longer as you rotate. So if you just drew a straight line, that wouldn't represent taking a point and having it rotate. It's like it's almost spiraling. It's not quite spiraling, but as you rotate, it's going out further and further. So it's not like a full spiral, but it's like that little section is acting like a spiral.
Okay.
It's not. It wouldn't be straight.
So it kind of acts like what was it, the cycloid?
Yeah. Yep. And it's the same thing up here. As you rotate from here to here, you go from 3 to 6. And another reason why it's not straight is because the graph that's generating this, it's not a straight graph either. The graph of sine has a curve to it. So when we use that to generate this, our new graph is also going to have a curve to it. Yeah. Right. And that's basically what this shape looks like. Does anyone have an idea or maybe a thought what that looks like?
Like a helmet?
A helmet?
Like medieval helmet. Like, you know, like the tall ones they use like back in the day.
Oh, okay, I got you, yeah. Okay. So kind of like maybe a helmet. Any other thoughts?
Like a guitar pick.
A guitar pick?
Upside down heart.
Yeah, it looks exactly like a heart. How could you not notice that? So especially if you color it in red. Okay? So it looks kind of like a heart. And because of the exact appearance of a heart from my picture, that's just the name that we call this, which is a cardioid.
Cardio?
Cardioid.
Oh.
Okay? Now, depending on the window you set on the calculator, it can look more or less like a heart. Sometimes if you squish it, it starts looking more roundy, more like rounded. But let's type that in and see what it looks like. So this particular one was 3 plus 3 cosine. Oh, no, what was it? Sine. Which one was it? Sine. 3 plus 3 sine. Anything in that format, a number plus or minus a number, and then sine or cosine. Okay, either one. That is a cardioid. What's that?
What was the equation in the hard one?
3 plus 3 sine. So I'm going to type that in. I'm going to go to polar. Type it in. And let's clear that. 3 plus 3 sine. Now, if I don't set a good window, it probably won't look much like a heart. Yeah, so that one my window there is really kind of squishing it. So what I might want to do is try zoom square. See if I can make it look a little better. All right, well, it doesn't look as squished. But depending on the window you set, you get a shape that kind of looks like a heart. I kind of exaggerate it and make it look more like a heart. But that's called a cardioid. Now, the bigger you make these two numbers, like 5 plus 5 sine theta, That's going to give you a bigger cardioid. And if you start, oh, that's not that one. Well, if you start to look at it, you might be able to figure out what these numbers are doing. Okay, where do you see the 5 and where do you see the 3? Well, in the cardioid, if you look at the height, what did the height on our cardioid go to? If you look at the origin up to the top.
0 to 6.
Yeah, it went 1, 2, 3, 4, 5, 6. And we had a 3 and a 3. So if you measure from the origin to the top of the heart, it's double that number. Okay. This one was a 5, and it goes all the way to the top of the screen at 10. So you can kind of start to get an idea of what these things are doing. Now, what's the difference between sine and cosine? Think of them on an XY graph. What's the difference? Yeah.
Sine's the y value, cosine is the x value.
So how about in terms of a transformation? How do sine and cosine relate? Right, we're shifts of each other by pi over 2 or 90 degrees. So now translate that to polar. What do you think is going to happen when I change sine to cosine if you change it by 90 degrees? What is that going to do in polar? Yeah?
Is where the heart occurs. Are going to move.
Can you describe like what kind of transformation it would be?
It would be like a rotation.
Yes, it will be a rotation of 90 degrees. So we have to kind of translate that thinking into polar. When we translate 90 degrees in rectangular, it moves it left and right. In polar, that's a rotation. So here's cosine. And what it did is it rotated it. I guess you could think of it as it rotated at 90 degrees clockwise. I don't know, like to me that looks more like a heart on its side, I guess. Okay. Now, if you start changing the two numbers and you don't have them equal, that's no longer a cardioid. Okay? It falls into a family of functions, but you kind of start getting it looping in on itself. Okay? And according to our book, that's not the definition of a cardioid. The two numbers have to be the same. So these kinds of curves that we're looking at, there's a whole family of curves in polar called limacon curves. Right? And cardioids are one type of curve that we can look at. Okay, we'll look at a few others. Yeah.
I was going to say limacon.
Yeah, yep. So there's all kinds of curves we can look at. Okay, if you reverse it and you make the first number bigger and the second one smaller, I think it starts to make the indentation on the heart less, and it starts to kind of smooth it out. Yeah, so it doesn't dip in as much. Okay. All right, so any question on cardioids? Remember, your theta min and your theta max does need to go from 0 to 2 pi. If I go 0 to 4 pi, what's going to happen when I draw it? Yeah?
It's going to be like a blank. It's not going to complete the full circle.
No, that's going to complete the full circle.
Twice as much.
It's going to go around twice. So you might see it, you might not see it. There's once. Yeah, you can see it. It's making it a little thicker because it's going over it again. But it's not going over it again in exactly the same spot because of the way it's counting or the way it's rounding or something. That's why it looks a little bolder. If it went over it in exactly the same spot, you wouldn't even be able to tell. So it's just like 1 pixel off or something. It's probably because of rounding. That would be my guess. All right. So let's take a look at now, how do we take a polar equation and change it to rectangular? Well, I kind of just showed you the other way, with y equals mx plus b. I took a rectangular equation and I made it polar. Now we're going to go back the other way. Well, there's really 4 different formulas that we've learned when we've been working in polar and rectangular. We've got the x equals r cosine theta, y equals r sine theta. We also have the Pythagorean theorem to find the radius. And we have this inverse tangent y over x for theta. So all of these formulas allow you to change one thing into another thing. And sometimes we have to use multiple formulas to convert something between polar and rectangular. So we're going to take a cardioid, 3 plus 3 sine theta, and we're going to convert a cardioid into rectangular. Doesn't mean we're going to be able to type it in on the calculator, though. We're going to get a formula with just x's and y's, but you won't be able to type it in. Because first of all, a cardioid is not a what? It's not a function. So really, there is not a way to graph it technically on the calculator unless you break it into multiple pieces and graph each piece separate. Okay. All right, so let's see if we can convert this to rectangular. Okay, in rectangular, what are the only 2 letters that you are allowed to have?
Excellent.
Yeah, so we got to get rid of everything here that's not an x or a y. So 3's are fine, but the r is not fine, and the sine theta, that's not fine either. Well, let's start with this. What could we substitute in for sine theta to get rid of it? Yeah.
Y over R.
Yep, we could substitute y over r. Now I know that that introduces another r. I mean, that's okay. Let's just try to get rid of sine, and then we can try to get rid of the r's. All right, so now we've got 3 plus 3y over r. Now, I generally don't like to have any fractions, so what could we do here that would get rid of all my fractions? Yeah. Yeah, we can multiply everything by r. And can you tell me what that'll give me when I do that?
R squared plus, I mean, is equal to 3 plus
3
R
r, yep,
plus 3y.
plus 3y. Yep. Okay, so now we have r squared equals 3r plus 3y. Well, 3y is fine. We're allowed to have x's and y's. R's we can't. So let's go back up and see if we can find a formula for r squared.
X squared and y squared.
X squared plus y squared. So if r squared is x squared plus y squared, then what could I change r to?
X.
Can't you change that to the square root of x squared plus y squared?
Yep. And you might think there's other things you could change it to looking at the formulas, but you don't want to introduce a sine or a cosine back into the problem. So you probably wouldn't want to use the top 2. Or the one on the right, because that's a tangent, but the one on the right doesn't even have an r. So we shouldn't even be looking at inverse tangent. All right. So we definitely want to use the one that just has x's and y's at this point. And then plus times y. Oh, no, I already did the y. Sorry, that's not there. And that's it. So you have r squared equals 3, oh no, I didn't write it, plus 3y. That's the part I meant to write. And there's nothing there that's not an x or a y. You can't graph that because there's no way to get y by itself. But that is what a cardioid looks like as a function. So it's actually much simpler looking than polar. Yeah.
Is there no further simplification we can do?
Not really. There's nothing else we can really do with that. No. Because you get some terms that are squared, some that are not squared, so there's no like terms to combine.
I have an idea.
Yep.
By subtracting subtracting the 3y to the other side, you get, and subtracting the x squared plus y squared to the other side, you'd have negative 3y alone, and then you could divide by negative 3.
You could, and you'd get y equals, but you'd still have y on both sides. You'd have y on the left, and you'd have a bunch of y's on the right.
Yeah.
So, yeah, that's about what we can do with that. So any questions on converting a polar equation to a rectangular equation? Okay, just use those 4 formulas right there. Okay, now let's look at how we can change a polar equation to a parametric equation. Okay, so this is polar, parametric. So one thing we have to remember when you go from polar to parametric, polar uses what letter as its variable? Yeah, theta, and parametric uses t. So at some point, we got to change thetas to t's. That's not a major part of the problem, but at some point, we need to do that. Okay, so graphing polar equations in parametric. All right, let's just take a cardioid. So I'm just going to try to draw my cardioid. Something kind of like that. Let's fix that a little bit. That's okay. Okay, so when we write something in parametric, how many equations do we need? Yeah.
X equals y equals.
Yeah, we need an x equals, and we need a y equals. So there's some formula to generate this picture. Let's say r of theta equals, I don't want to use an actual problem, but there is some formula for this picture. So I'm just going to say that's the formula for that picture, r of theta.
Didn't we already find that earlier?
We don't know. It's just a generic polar equation.
Oh, okay. So we don't use the one we found.
No, just in general. It could be any polar shape at all. To break this down into parametric, you got to start thinking about, you can't be thinking about a radius and then an angle of rotation. You're going to imagine you have a point on this curve and think how far right and how far up did you go. Okay, that's parametric. How far right, how far up. So we need to figure out those two things. So what do you think I'm going to draw here that's going to help you figure that out? Yeah?
Triangle.
Yeah, I'm going to make a triangle out of it. Okay. This bottom side is x. That's y. Now, the side in blue. It is my hypotenuse in the triangle, but what is it in the polar shape? It's my what?
Radius.
It's my radius. It's the distance that I moved from here to here. How do you get this radius? Like when we did the cardioid, how did we calculate how far out to go? Yeah. Well, we don't know x and y. So like, how did I know on this cardioid to go out 6 units? What gave me 6 units? Where did the 6 come from? Yeah.
Adding the 2 things in the equation, like you added 2 3's and you got 6.
Wait, they gave me an equation, right? They give you, in polar, you have a formula for finding the radius. It's not a constant radius. If it was a constant, it would be a circle. It's a radius that's changing, but it's very predictably changing. There's a formula to calculate it. And that formula is r of theta. It's a function in terms of an angle. So they'll give you a formula to calculate the radius. You just use it. That's your R, which will give you your hypotenuse in the triangle. Okay. So this is R of theta. That's the hypotenuse. And so if I can just go back, just look at this one more time. So like we had a point, at one point we were right here. That distance from here to here, if I know this angle, let's say that angle was 45 degrees. All I have to do is fill in 45 degrees for sine, multiply by 3 and add 3, and it will calculate the radius at that point. Okay? So the formula calculates the radius, and the radius is really the hypotenuse. Okay, so use the formula to find the hypotenuse. All right. I think that's what I wrote right here. Yeah. All right, so now let's start to think about how we would get x and y. Let's let that be our angle, which is theta. So there's theta. I need to change this to a t at some point. So we can keep it a theta for now. What would be my formula for x based on using adjacent over hypotenuse? Yeah.
R cosine theta.
But r we don't know. We have to use a formula to find it. So instead of r, we would have what?
The tan theta or no.
How are you finding r in this? What's the formula to find r in that picture?
The R theta.
Exactly. So it's some function of theta. And then what did you say came after that to get the x part?
Oh, R cosine theta.
No, not r. You can't use r because we don't know r. We have to use a formula to find r. So we have r of theta times what?
Cosine?
Cosine theta.
Oh.
Okay, if r was a fixed number, you could just fill it in, but you don't know what r is. The radius is a constantly changing number that you're going to have to get from the formula that made the picture of your shape. And how about y? What's the y value going to be of this point?
Isn't it r theta sine?
Right. It's whatever the radius is for that amount of angle that you're rotating, which you won't know until you plug it into the formula, times the sine of theta. And that's basically how you change parametric, polar to parametric. The only thing I have to really do is instead of writing r's and thetas, we should use the notation for parametric, which is f's and t's. Okay, so just changing the notation. T does represent theta in this case. It's just in parametric. You don't call it theta. You have to call it t. So this becomes t. Just a change in the name of the variable. That's all.
Wait, so would it be like the cardioid function turn into t or theta turn into t?
Theta just becomes called t
Okay.
because it's just the name of our variable.
So instead of r theta, it would be ft.
Yeah. Yep. So we just call it some function in terms of t, and t was originally called theta. So it's just some function in terms of theta. So this is essentially your r, and this is also your r. I just can't write r there because I don't necessarily know the fixed value. It's a calculation I have to do because it's changing the size as the more and more you rotate. Again, if it doesn't change size, then it's a circle, right? But it is changing size. And just because it changes size doesn't mean it's a cardioid. Spirals change radial size. Flower petals, which I'm going to show you an example of, they also change size. So let's see if we can use this idea to change something to parametric. Okay, let's try this one. So we have 7 sine 2 theta. That's your R. That's how you calculate your hypotenuse in your triangle. Based on the hypotenuse, I want you to tell me the base of the triangle and the height of the triangle. So to find the base, what do you always multiply your hypotenuse by?
You multiply it by R?
Well, the hypotenuse is R. So my question is to get the base.
You multiply it by theta. Well, if you have the hypotenuse, you want to find out the x and y, you can do that, like...
How do you find the x when you know the hypotenuse?
You use the equation for... Would you use the new equation?
Yeah.
So that would be... To find x of t equals f of t of cosine t, so r equals function of theta, so we would do like 7 times t cosine t.
No.
Not quite. So there's a trig function you always multiply the hypotenuse by, and it gives you the base of the triangle. Then there's a trig function you multiply the hypotenuse by, and it gives you the height of the triangle. Which function do you multiply the hypotenuse by to always get the base, the horizontal? Yep, cosine. And this is your hypotenuse. It's a constantly changing hypotenuse depending on what you plug in for theta. So the base is the hypotenuse times cosine.
And we can replace the thetas with...
Yes, you're right. I should put t's there. Yeah. Those should turn into t's. So sine 2t, cosine t. And what do you multiply the hypotenuse by to get the height of a triangle? Yeah?
We'd multiply it by sine t.
Sine. So here's your hypotenuse. Multiply the hypotenuse by sine, and that will give you the height of a triangle.
I got the graph for it.
Yeah, let's take that in and see what it looks like. So go to parametric, type in 7 sine 2t, cosine t, and 7 sine 2t, sine t. For my window, that might be okay. Let's just try it. Yeah, a little jagged, but that's the idea of what it should look like. Yeah. And we can confirm we did it correctly because we can go back to polar, type in the original problem they gave us, and see if it looks the same. 7 sine 2 theta. 7 sine 2 theta. Yep. Now, I think I still have it set on 0 to 4 pi, which is why it traced it twice. I should fix that. But there's your two graphs. Okay, on the right is polar, on the left is parametric. You never know the difference. You can't tell when you're looking at the final result. Okay, but that particular graph is called a 4-petaled rose, and each petal has a length of the number in front. So this petal is 7 units long. And when I say 7 units, just to be clear. Okay, that's 7 units from here to there.
So
7
it has a
units.
hypotenuse of 7.
Yeah.
R thetas?
What is it?
But if you say that's the hypotenuse, are we saying that's R equals that, or R theta equals 7?
So I'm just saying if you take and draw 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 7. So I just drew something exactly 7 units long. If you position that just right, it will come out to exactly the length. I didn't rotate it perfect, but you get the idea.
Well, like,
It's the length of the pedal.
for connecting it to the other stuff, doesn't equal R, doesn't equal R theta, then
Well, it is R. It's the longest possible R value you ever get. You never get more than 7 units away from the origin in a 4-pedaled rows type graph.
so we need to worry about how it relates to R theta.
Yeah. It just tells, it's the maximum distance you ever move away from the origin
Okay.
in any graph. The bigger you make R, the bigger you make the number in front, the bigger the pedals get. If you start changing like the 2 to a 3 or the 2 to a 4, you can start changing the number of pedals. Okay? Even numbers always double the number of pedals. So if you put in like a 5 theta, well actually let's do even, I said. Put in a 6 theta, you're gonna get 12 pedals. You should probably try to smooth that out a little bit by increasing the theta step. That's a little jagged. But an even doubles the number of pedals, and an odd gives you exactly that number. So a 5 theta would give you 5 pedals. And again, I should stop it from tracing twice.
Could you go up on the second screen?
Yep.
Thank you.
So the last thing, we'll look at it a little tomorrow too, is a spiral. Okay, if you do R equals theta, you get a spiral. It's the simplest spiral you can have. It's called the spiral of Archimedes, and it's a spiral where the radius is exactly the length of the angle. So if you're at 90 degrees, the radius is 90. If you're at 180 degrees, it's 180. If you're doing it in radians, what would be the biggest, or what would be the furthest the spiral would ever get from the origin in one revolution?
360?
5 degrees, it would be 360. About
2
pi.
pi.
2 pi, yep. So if I do one revolution, and I set my window to go 2 pi units in every direction, that should be plenty to see one revolution of a spiral.
What's your answer?
The only place that you actually need the maximum amount is on the positive x-axis. That's where it always is furthest in a full revolution. What if I wanted to see 2 revolutions of the spiral?
4 pi.
Yeah, I'd set it to 4 pi, and then I'd have to make sure that my x max goes to 4 pi. Probably even have to adjust the line in a little bit, because it's probably going to go off the screen. Yeah, there's a few things I need to adjust. I didn't adjust the other ones to 4 pi. But if you did, you would see 2 revolutions of the spiral. Yeah.
Is that related in any way to the golden ratio thing?
I'm not actually 100% sure. I don't know. It might be. I'd have to look it up. But we can spend more time with the spiral tomorrow, but I mean, that's pretty much it. That's a spiral. There's no easy way to convert that to a function because it definitely fails the vertical line test. So, function, you've got to really graph this in polar. Alright, so that's homework for tonight. Actually, I can just make that a little simpler. 37 to 49 odd. Okay, so we'll take a look at that tomorrow. We can play around with the spiral a little more or some of the other graphs because we don't have any new material for tomorrow. So this was the last day of new material
Yeah.
for this week.